Getting into chapter 15, we are going to look primarily at the applications of equilibrium. So we're not really learning a whole lot of new things, we're just going to learn to interpret and analyze them in new ways. Here are some learning objectives that go along with it. We need to perform calculations, a new vocab word for common ions. So here's a weak acid problem. It's an equilibrium. Calculate the pH and percent dissociation of the acid in each of the following solutions. Now part A should look very familiar. It's just a weak acid by itself. So if we just set up our ice chart, and we have our weak acid dissociating, like so, and we know that this is 0.2 molar, 0 and 0. So this should be pretty familiar from chapter 14. We solve this. We have a Ka 1.8 times 10 to the negative fifth equals x squared over 0.2 minus x. X comes out to be 0.00189. pH coming off of that is going to be 2.72, because that is my hydrogen value. And then to get the percentage here, we look at our x value, how much dissociated, 0.00189 over my original 0.2 times 100%. And the percent dissociation here, it's really small. It's a 0.945%. So a simple weak acid problem, pH is 2.7, and my percent dissociation is a little less than 1%. This is going to change a lot. The next problem here says, what if I had that same solution in a 0.5 molar sodium acetate? So let's take a look at that one. Okay, the first thing we need to see here is sodium acetate. If we get our same balanced equation ready, we still have the weak acid dissociating, but we notice that the sodium acetate has an acetate ion in it. This sodium here is a spectator, and this acetate is actually over here. So when we set up our chart, I still have the 0.2 molar acetic acid. However, and I don't have any hydrogen, but I do have now, I don't have 0 acetate, I have 0.5. This is what we mean by a common ion. We have some of the products to start with. Now it still has to shift left in order to get some hydrogen. But when we have a common ion, adding some product to start with actually shifts this equilibrium back towards the reactants, so these x values are going to be smaller than they would originally be. That means these x values are going to be negligible. Whenever you have something on both sides, your equilibrium value is going to be the exact same value as your initial value. Those aren't going to change. But the hydrogen being 0 is going to change significantly. That's still going to be x. So we don't have a large equilibrium problem to solve here. With the solver, we can do this with a calculator. 1.8 times 10 to the negative fifth, that's my Ka, now equals x times 0.5 all over 0.2. That x value comes out to be 7.2 times 10 to the negative sixth power. And that is the hydrogen, so that pH is going to be 5.14. Okay. Which is significantly higher than the last problem. Now, why is that? Well, we added our same acetic acid but we added some conjugate base to it. So if we're adding some base, we do expect the pH to be a little bit higher. Percent dissociation is going to be the same as before. 7.2 times 10 to the negative 6th is how much dissociated. I still had 0.2 of the acid. We're not worried about the conjugate. We just want to know how much of the acid broke off. And we get a percentage of 0.0036. So incredibly small. That percentage, in the presence of a common ion, we can see here, this is our proof, the equilibrium shifted. That X value is almost, it's a lot smaller than it was before. It's negligible to the acetic acid and the acetate ions, and then the percentage went from about 1% to 0.003%. Okay, in the learning objectives for section 2, we get our first look at this word here, buffer, which is just an acid-base conjugate pair that are in the same solution together, much like we saw in the last problem. It's a common ion problem, and then we will use those to neutralize acids and bases in different solutions and titrations. So calculate the pH of a solution that contains 0.25 molar formic acid and 0.1 molar sodium formate. So very similar to our last problem. Let's take a look here, and we see we have HCOOH dissociates into H plus HCOO minus. This is always the equation we want. We want the acid equation because we're after pHs. To do that, we need to see that my formic acid is 0.25 molar initially. My hydrogen is 0, but my formate, since my sodium here is a spectator, that's COOH. We need to recognize that that is a conjugate, and we have 0.1 of my formate ion. So we go through our chart, minus X, plus X, plus X, and when we have the common ion there, and we're going to call this a buffer now, because it's a conjugate pair. It's not just a common ion, it is a conjugate pair. We get that, and Ka 1.8 times 10 to the negative 4th equals X times 0.1 divided by 0.25. And our X value comes out to be 4.5 times 10 to the negative 4th. And our pH is 3.35. Same problem, but this one says let's solve it now using the Henderson-Hasselbalch equation. So Henderson-Hasselbalch, this is worth going through here. We take a Ka, let's do our formic acid, products over reactants, we get the hydrogen, the formate ion, all over the formic acid, HCOOH. To take a pH, we would take the negative log of the hydrogen. What the Henderson-Hasselbalch does is it takes the negative log of both sides. You don't need to know how to rearrange this equation, but if I take the negative log of my Ka, I can, what I can do is, let's just look at that, and then the negative log of that side as well. We can rewrite this as the negative log of the Ka, and then we can pull this out, negative log of the hydrogen plus, well, minus, because it's a negative log of the A minus over the HA, the base over the acid. And since we're talking about formic acid, let me just do this the right way and say HCOO minus over HCOOH. Okay, This just lets us separate. We can take the negative log of that whole big thing, take the hydrogen out. The reason we take the hydrogen out is because this is a pH. And when we have negative log of a Ka, we're going to call this a pKa. So we get a new term there. And it gives us this equation, and when we rearrange it, we get pH, we move things to different sides, equals the pKa plus the log, and it's just like we always do, the base over the acid, HCOO minus over HCOOH. Just like any Ka expression, Henderson-Hasselbalch is no different. So it takes that and it rearranges it. You can solve this problem either way. We've already solved this problem with the Ka expression, but there are some benefits here to the Henderson-Hasselbalch. So let's take a look here. My pKa, if we took the negative log of this, is going to be 3.74. And that pKa is going to be a good benchmark for a lot of our acid-base problems moving forward. Plus the log of my base is going to be 0.1. That's my sodium formate. Sodium is a spectator. And my acid is 0.25. So my pH, when we solve it using the Henderson-Hasselbalch, is going to come out to be 3.34, which is within a sig fig of the last problem we solved it in with the Ka expression. So we will use the Henderson-Hasselbalch a lot. Okay, in this problem we're going to look at the same solution we had in the last problem. And let me highlight this so you can see, because classifying here becomes the most important thing. Here we have our formic acid and our conjugate base, and we don't care about the sodium. Sodium's a spectator. So that's an acid and a base conjugate pair. That's a common ion. That is a buffer. They do not react with one another. Same concentrations as before. Now this one says, calculate the pH after the addition of sodium hydroxide. Sodium hydroxide is a base. It will react with the formic acid. Buffers since they have a conjugate acid and base in them, the acid portion will react with any bases that are in, and then the conjugate base will react with any acids that get added. Now that's not this problem, but here we can see the formic acid is there to react with the sodium hydroxide that was added to the system. A couple of things about this problem that make it challenging are the volume changes. 10 milliliters, and then it says we have 500 milliliters of our conjugate pair buffer. So we need to keep track of volume changes and moles. This will be more akin to chapter 4, where we have to do everything in moles and then do some volume changes. Our first reaction here is a neutralization. Okay. Our neutralization reaction is going to be that sodium hydroxide that was added. Sodium's a spectator, and it's going to react with our HCOOH, our formic acid, acid-base reaction. This is going to make water, and the conjugate, HCOOH. HCOO minus. It's conjugate base. Now this is not an equilibrium. Acid-base reactions are limiting reactant problems. They go to completion. Now we need to keep track of the moles of everything. So all of these terms here are going to be in moles. We had 500 milliliters of the 0.5 molar acid, 500 milliliters of the 0.1 molar conjugate. What that does is it gives me at the very beginning 0.125 moles of acid and 0.05 moles of my conjugate base. And then here with 10 milliliters of my 6 molar sodium hydroxide, which is really concentrated, but I only have 10 milliliters of it, that gives me 0.06 moles of the sodium hydroxide. Now 1-to-1 ratios are really nice here because we can see that the hydroxide is going to go away to 0. There will be nothing left. So we have to subtract that from my reactants, and we're going to add that to my products. And of course we don't care about the water. Okay, so my formic acid is now 0.065 moles, not molar, just moles, and then my conjugate is 0.11 moles. Now we need to get these into molarities, so we have 510 milliliters, so 0.51 liters. And here we have, at the leftover, we have none of this left. The sodium hydroxide is gone. I have a 0.127 molar formic acid. Okay, and that's my weak acid. And then I have 0.216 molar of the conjugate base. All right. Now, since that's an acid-base pair, a conjugate pair, we can use Henderson-Hasselbalch to solve the rest of this problem. So just like we did before, if I have molarities of both the acid and the conjugate, the X values are going to be negligible. We get a pH equals a pKa. pKa is 3.74 plus the log of the base over the acid. So 0.216 over 0.127. All right. And here we get a pH of 3.97. And if we go back to the last problem, we can see that the pH was, I think, around 3.3. So it didn't change much, even though we added the sodium hydroxide, because it was neutralized and we had a buffer. The buffers resist changes to pH. It makes sense that it went more basic because we used up some of our acid and it turned into some more conjugate base. So I have a little bit more conjugate base than I do the acid. So we've got a pH of 3.97, which is slightly above our 3.74 pKa. Take a look at this problem. We see a solution is prepared by adding 31.56 grams of sodium cyanide and 22.3 grams of HCN to 600 milliliters of water. That should clue us in that we have a buffer, because that's a conjugate pair, and we have the Ka there for HCN. So what is the pH of this solution? The first problem here in A is a common ion problem. So we can, it's a buffer. So we can use Henderson-Hasselbalch or the K expression, either one. First we need to know how many moles we have and what the molarity of those two things are. So let's do the HCN. We have 22.3 grams and 27.03 grams per mole. Is 0.825 moles. Now I'm going to want those moles later, because when there's volume changes in the next part of the problem, we're going to want to see how many moles of everything we had. We divide that by the 600 milliliters, 6.6 liters, and we'll get a molarity of the HCN is going to be 1.38 molar. And then for the NaCN, we have 31.56 grams. .49 grams per mole. 0.644 moles over 0.6 liters, and we get 1.07 molarity. Okay. So from there we can go either into the K expression, I'll do both, or into Henderson-Hasselbalch. So we use those molarities, and the first one would just say, okay, we have HCN dissociating into H plus CN minus. We have 1.38 moles of HCN, and we have 1.07 moles, or molar, of the cyanide. Since we have a common ion, we have both things. Neither of those X values are going to change. We don't really need the whole ice chart, but just to kind of show us there, we say minus X. This is still going to be 1.38. This will be X, and then the cyanide will still be 1.07. Okay, those aren't going to change. So when we plug them into the K expression, we get Ka equals, and you can skip that. You can just go right down to the bottom here. You know that the hydrogen's X and those other two aren't going to change. There's no need to really show that. .07 over 1.38. We have the Ka expression in the problem. The other way to do that is to use the Henderson-Hasselbalch. And that says our pH equals our pKa, and our pKa in this case is 9.21. It's the negative log of the Ka. So pH equals 9.21 plus the log of the base over the acid, just like it is in this expression. We do the cyanide over the HCN, products over reactants. That's where it comes from. It's the 1.07 over the 1.38. We can do it that way as well. So if we solved for X and then got the pH, or if we just went right into the Henderson-Hasselbalch and got the pH, we'll get a pH of 9.10. And we can use this, let's just look at this Henderson-Hasselbalch equation again. We can use this if I have base over the acid, and this ratio here is less than 1, means I have more acid than I do base. That means my pH is going to be a little lower than this pKa. It's a little bit more acidic than this pKa, because when this ratio is 1, the pH is the pKa, because the log of 1 is 0. So mathematically here, if I have more acid, my pH will be a little bit below that. So we can use that as a guidepost for estimations. Okay, so that is the buffer all by itself, the common ion problem. Let me clear this out and look at part 2. Says, or part A, part 2, what is the pH after the addition of 50 milliliters of 3 molar HCl to the buffer that we already have? So a couple things. One, we have another volume change. That's where we really want to work in moles. And we're adding an acid. So the first thing we have to ask is, what will acids do? We need a reaction. Acids are going to react with bases. The base part of my buffer is the Cn-. We don't care about the sodium. The sodium is going to be a spectator, but it's the Cn-. Acids react with bases. So H plus Cn- make HCN. That is my reaction. This is going to be a neutralization reaction, which is not limiting it's a limiting reactant problem. It's not equilibrium. It's a stoichiometry problem. And we want to do all of this in moles because there are volume changes. So when we say we have 50 milliliters of 3 molar HCl, we have 0.15 moles of HCl. And that's where my hydrogen's coming from, because that's my main source of hydrogen, is that strong acid that was just added. The cyanide, we calculated on the last problem, how many moles of the sodium cyanide do we have, was 0.644. We don't want the molarity, we want the moles, which is that intermediate step before we divide it by the 600 milliliters. So 0.644. Now my products here are not 0. We had some hydrogen cyanide, it was 0.825, or hydrocyanic acid rather. Those are how many moles we had of all of those three before we got the molarities. So now we have a limiting reactant problem. We can see that they're all going to be 1-to-1 ratios. We can see that the hydrogen is going to go to 0. We subtract 0.15, and then we add 0.15 to the products, and we'll get some new moles. My cyanide is 0.494 moles, and my HCN is 0.975 moles. My new volume is not, originally we had 600 milliliters, and then we just added 50 more of the acid, so 650 liters, so we get both of those. And we'll get new molarities of our the resulting solution. This is 0.76 molar, and my HCN is 1.5 molar. Okay, so now we have to analyze, and this is not always going to be the same thing. We have to look at what is left. My hydrogen is nothing. I have cyanide and HCN. Cyanide and HCN together make a buffer. So not every problem does this, but this one does. We are back to a buffer. We have a conjugate pair. So we want to take these molarities. In order to solve the pH, we neutralized some of the base, but now to get the pH, I have to do a buffer problem. pH is pKa plus log of the base over the acid. Oh, let me just jump right in. So pH is the pKa we calculated before, is 9.21 plus the log of my base, which is the cyanide, 0.76, over the acid, 1.5. Now we added more acid, so this pH should be lower than it was in the last problem. We solve that, we get it's 8.91, but we can kind of see, even though we added a strong acid to this problem, the buffer neutralized it and then was able to regulate the pH and keep it really close to that pKa. We have more acid, so it's a little lower than before, but it keeps it regulated pretty close to that value. So this problem took 2 steps. The first one, we had to do a stoichiometry problem to neutralize the acid that was added, neutralize the acid with the conjugate base, and then at the end we had a conjugate pair, so we had to solve a buffer problem. And here's we mentioned it before, but this is really our guidepost for that pKa in the Henderson-Hasselbalch. When we look at our reaction, or our equation, pH equals pKa plus the log of the base over the acid. I'm just going to do the conjugate base over the acid. We'll do that. And this question says, what is the pH? Here's propionic acid. What is the pH when the acid and its conjugate are equal, when those molarities are equal? Well, when these guys are equal, A minus over HA, that gives me the log of 1. Well, the log of 1 is 0. At this moment, when those conjugate pairs are equal, our Henderson-Hasselbalch equation gets reduced to the pH equals the pKa. And that's a very important point in a titration. When we start out with only an acid, the point where these two are equal is called the midpoint. It's halfway to the equivalence point. So this is a really important point here, and that's kind of where the buffer gets regulated for any acid. That's the pH of that particular buffer, is the pKa. So the pKa of this particular problem is 4.87, so that will be my pH when those are equal.